Hi, this is Chapter 6, Section 1 for Honors Physics. This one has to go out to Courtney. Courtney was just so thrilled with making the top three. She said she drug Bridget Gray said you drug her in here and had to show her your name, and you were just so proud of that. So, and you should be proud of that. Good for you. Okay, so let's take a look at motion in 2 dimensions. Um, and again, we're going to use vectors. We're going to use Newton's law. And we're going to use our vector diagrams to analyze this motion. So with a projectile, this is the first one we want to look at. Projectile's horizontal motion is independent of its vertical motion. That means that if it's moving horizontally at 2 meters per second, it doesn't matter whether it's going up or going down or going sideways. Horizontal motion is independent of the vertical motion. So we want to look at how the vertical and horizontal motions of a projectile are related, because they are related, and how this relationship between the height, the time in the air, the initial velocity, the horizontal distance traveled, all these things tie in together. Really, it ties in real beautifully with the vector diagrams, or excuse me, the velocity diagrams. We will do some motion diagrams as well. So we're looking at the idea of projectile and trajectory. So you've seen projectile motion before. If you see a golf ball being hit from a tee, frog hopping, free throw shot with a basketball, they all kind of follow this general pattern. Baseballs, arrows, they each rise and then fall following a curve called a parabolic path. So we want to see if we could identify and look at this parabolic path. The object shot through the air is called a projectile. And the projectile could be a number of things. It could be a football, it could be a drop of water, whatever. So, no matter what the projectile is, after a projectile has been given the initial thrust, if we could ignore air resistance, then it will move through the air with only the force of gravity acting on it. The force of gravity is going to pull it back towards the Earth in a parabolic path. Its path through space is called the trajectory. You can determine an object's trajectory if you know the initial velocity and you know the launch angle. There are 2 types of projectile motion. One is horizontal. I showed you that in class. If I knock a ping pong, if I flick the tennis ball off of the table, it's going to go in a projectile motion away from the table and fall. We haven't done one where we're shooting something up in the air. That's the next thing. Here's one that is just coming straight off of the table, similar to the one that I showed you in class. And let's see if I can get it to play. Where is it at? There it is. There.
Consider the trajectories of 2 softballs. One was dropped and the other was given an initial horizontal velocity of 2 meters per second. What is similar about the 2 paths? Look at their vertical positions. During each flash, the heights of the 2 softballs are the same. Because the change in vertical position is the same for both, their average vertical velocities during each interval are also the same. The increasingly large distance traveled vertically by the softballs, from one time interval to the next, shows that they are accelerated downward due to the force of gravity. Notice that the horizontal motion of the launched ball does not affect its vertical motion. A projectile launched horizontally has no initial vertical velocity. Therefore, its vertical motion is like that of an object dropped from rest. The downward velocity increases regularly because of the acceleration due to gravity. You can see here separate motion diagrams for the horizontal and vertical motions. The vertical motion diagram represents the motion of the dropped ball. The horizontal motion diagram shows the constant velocity in the x direction of the launched ball. This constant velocity in the horizontal direction is exactly what should be expected because there is no horizontal force acting on the ball. In this figure, the horizontal and vertical components are added to form the total velocity vector for the projectile. You can see how the combination of constant horizontal velocity and uniform vertical acceleration produces a trajectory that has a parabolic shape.
Okay, continuing on. Now, how about angled launches? When we're going to launch a projectile at an angle, the initial velocity is still has a vertical component, but it also has a horizontal component. So if the object was launched upwards, like a ball tossed straight up in the air, it rises, it slows down, it reaches the top, it then descends, and it starts picking up speed again. We've seen that before. If we have a horizontal motion, the horizontal motion is constant. There's nothing that slows it down. Once it has a velocity from left to right, unless there's a force acting on it, that velocity from left to right is independent of whatever's happening on the up and down motion. At each point of the vertical direction, the velocity of the object as it's moving upward has a magnitude as when it's moving downward. In other words, basically from here to here is the same as moving down like this. The only difference is the direction of the arrow, but otherwise we're going to see this motion here. So we put the two of them together with the upward motion getting smaller and smaller and smaller, going to 0, then it becomes a downward motion. The other motion, the horizontal motion, is staying the same the whole time. We end up with this kind of parabolic shape. A couple things we could figure out. One is we could figure out the range. Where does it land? We could figure out the maximum height. How far up does it go? We're going to have to figure out the time, which is probably the first thing we're going to do. How long does it stay in the air? So all these things are things that we traditionally will calculate with a problem like this. So we have the maximum height again that we can calculate if we need to. And then the range, which I've already discussed. Again, the last comment, not shown as the flight time, and again we discussed flight time. So with football punts, really the big thing is hang time. How long does a football stay in the air? It's not really how far it can go. Any punter could kick it down to the end of the football field. The big thing is how long can you keep it up in the air. Okay, so let's take a look at a problem. It says a ball is launched at 4.5 meters per second at 66 degrees above the horizontal. The questions that we're going to try to answer are the maximum height, the flight time of the ball, and how far does it go. So if we analyze the problem, we have to establish our coordinate system. So here we have our angle is 66 degrees, our vector, the initial vector, the initial velocity is 4.5. The ball will travel up, reach its maximum height, and fall back down. We can calculate the range, how far the ball went. We could calculate the maximum height, how high it got up, and we could take how long it took to fly the distance. So again, kind of repeating that. If we do a free body diagram, we got a dot representing the ball. What's the only force acting on it once it leaves on its path? In other words, we're not ignoring the force that got it moving. Once it left and was in the air, what's the only force acting on it? The answer is gravity. So this is the free body diagram. The free body diagram doesn't tell you what direction it's going in. It doesn't even tell you if it's in motion or not. It simply tells you what the force is that's acting on it. So here we have that doesn't tell us whether it's moving straight up, straight down, or at an angle. This is the only force we have acting on it. Notice that there is no horizontal force acting on it, so there's nothing to slow down the initial velocity in the x direction. This is only going to affect the y direction. So let's take this diagram and break it down. We're going to use this decomposition of a vector to look at the x and the y. We have our right triangle, 4.5 degree angle. We want to figure out what this leg is over here. This is going to represent, if this is the initial velocity, this is going to be the initial y velocity. Opposite over hypotenuse is the sine, so the sine of 66 times 4.5, we get 4.1 is the initial upward velocity. We want to figure out the Vxi, which is the horizontal velocity. We're using the cosine, adjacent over hypotenuse, cosine, 66 times 4.5 ends up being 1.8 meters per second. We're going to draw two velocity diagrams from this. We have a vertical velocity diagram and a horizontal velocity diagram. I would have liked to have drawn these over each other because the timelines are going to line up on both of these. So let's start though with the vertical velocity diagram. What's the maximum velocity? 4.1. What's the slope of the line? The slope of the line is the acceleration. What's the only thing causing acceleration here? The force of gravity, 9.8. So we know the slope of the line, we know the initial velocity. What can we figure out from this? Well, we could figure out the time, and we could figure out this area under here. This represents how high the ball went. So let's figure out the time first. We know that the slope is rise over run. The rise is, or the slope is 9.8, the rise is 4.1, the run is the time. We could calculate the time from the time that we launch it to the time that it gets to its highest point till it stops moving up and starts moving down, 0.42 seconds. If we want to figure out how long it takes to get all the way back down, that's twice the time, and we have 0.84 seconds. Now we want to figure out how high it goes. The area is half the base times the height, so half the 0.42 times 4.1. The highest this ball gets is 0.86 meters high. So we know the time it was in the air, 0.84 seconds is the total time it was in the air. We know how high it got. Now we want to figure out how far it went. Horizontal velocity. The acceleration is 0. There's nothing slowing it down. It starts at 1.8 and it's 1.8 for the entire time until it hits the ground again and stops moving. We simply have to figure out the area's base times height. So the distance traveled is going to be 0.84 times 1.8, 1.5 meters. It travels a total of 1.5 meters. It travels 4.84 seconds, and the highest it got was 0.86 meters. So that's how you solve this problem. Okay. If you want to go use the book answer, again, you have to figure out all the knowns and the unknowns. They're going to suggest that you use some equations. I'm not going to use the equations. We've already figured this out. They're getting the same answer, however. They got the initial velocity was 4.1 meters. It came back down at 4.1 meters. And so you have to go through all of the velocities, squares, and all this other kind of stuff. I'll show you this in class if you want to come in during an open lab, rather. I'll show you how this all works. Get the same answers that I got. I think mine way was much easier. If we want to figure out how high it got, again, you're going to use equations. And you have to solve for t. And again, this all calculates out. I will show you how that works. Okay, so that's the flight of the ball. The other thing I wanted to talk about briefly is what happens if we take air into account. So far, air resistance has been ignored in the analysis of projectile motion. We will pretty much ignore it all the time. Force in the air, though, can significantly change the motion. For instance, if you got a kite, if you have a parachute of a skydiver, consider water flowing from a hose. If the water is blowing in the same direction as the water's initial movement, the water is going to get a lot further. If it's blowing in your face, you're going to get wet. Even if the air is not moving, it could still have a significant effect. It could basically cause drag. For instance, if you have a paper falling to the ground, it's going to fall more slowly. So, that's it.